So we're going to take a look at Chapter 14 first and then Chapter 15 review. They're two separate documents. Review for an exam. The exam will be on Thursday. Yeah. Thursday, we'll have an exam, and then we'll jump into Chapter 16 on that day, and we'll be able to finish it because we won't have a lab that day. We can just take the whole thing.
Okay. Hey,
Tuesday.
so
Yeah,
the report, is the report due Thursday or not till we go to the next lab, right?
yeah, it should be when we go to the next lab.
Okay. I was making sure it was still like last semester.
Let me see if I put that in the syllabus correctly.
Okay.
Successful do. Right. Yeah. It's
Okay.
be on the 6th.
Okay. Thank you.
Last one. Okay, so let's take a look at Chapter 14 first. And number 1. All right, which of the following is a conjugate acid-base pair? Remember what's required for a conjugate acid-base pair? 2 things. 1, one hydrogen ion at a time. Okay. And 2, the conjugate base portion of the molecule has to be there before and after. Okay. So let's see which one's satisfied. HCl and OCl minus. What's wrong with this picture? Well, it meets that one okay. Only one hydrogen's lost, but the conjugate base is not the same. We stuck an oxygen in there, so that one can't be it. How about H2SO4 and SO4 2 minus? Well, we can stop with this one. 2 hydrogens are lost here. You can only have 1. Now, this part of the molecule is okay, but it should be like that. Right. So that one's wrong. How about this one? NH4 plus and NH3. That looks like a good candidate. Right. 1 hydrogen lost from here to here. There's ammonia. Normally what you would see, you would do is put ammonia in solution, and the ammonia would react with water. But if you put this in solution, say as the chloride salt would be a good way. If you did this, right, then this is just a spectator. So now you would have your acid, and it would release a proton and make ammonia. So that's a valid acid-base pair. It meets both conditions. D, of course, is all wet. That was actually a pun intended. Right? So how many hydrogens would you have to lose to get from here to here? 2. That would have to lose 2 hydrogens, 1 to go to water and 1 to go to hydroxide. So that's not a valid acid-base pair. Only this one. All right, number 2, I think. Let's see, I'm gonna have to scroll this one. I'm not even gonna bother with my magic wand. It never works on these things anyway. The hydrogen sulfate and bisulfate ion can act as either an acid or a base. Those are 2 different names for the same molecule. HSO4 minus. The The proper name is hydrogen sulfate ion, but we used to call it the bisulfate ion. It can act as either an acid or a base in water. In which of the following equations does H2HSO4 minus act as an acid? If it's going to be a Lewis acid, it has to donate a proton. So when we put it in water and it reacts with water, then it has to transfer that proton right here over there. And that makes the conjugate acid of water. And the conjugate base then would be sulfate ion. So it looks like D works for this one. Okay. What would it look like if it acted like a base? Well, in that case, the hydrogen would be transferred from water. It would be the acid. Transfer a hydrogen over here, and now you get sulfuric acid plus hydroxide. But that wasn't the question, of course. All right. Number 3. Okay. Let's see. Which of the following is the equilibrium constant expression for the dissociation of a weak acid? HOCl. By the way, how would we name this acid? It's an aqueous solution. Remember, this ion right here is the hypochlorite. So it'd be hypochlorous acid. And the K expression for this, for the K expression, we don't have to write the water in there. The water is going to be left out anyway, right? Because it's a pure liquid. So we would use the abbreviated form like that, and those are aqueous. So then the K for this one would be just this part, and then this part. Okay. So it looks like our A is the best one about all that bunch. All right. That's 3. Yes, looks like we're going to skip one at least. And 2. Okay, we're going to land on number 6. So we'll do 6 and 7 there without scrolling. Okay, a solution in which the POH is 12.1. And we're given POH equals 12.1. Would be described as what? Acidic, neutral, or basic? Well, let's see. We usually think of acidic or basic in terms of pH. So it might be more intuitive to determine what's the pH here. All right, so it would be 14 minus 12.1 would be what? 1.9? That would be very acidic. And it'd be on the order of stomach acid. So that would be A. Okay. Now 6. About 7. Which of the following indicates the most basic solution? All right, we've got a mix here. So in order to compare apples and not apples and oranges and bananas and grapefruit, we need to put them all in the same form. So I would go for pH. So if A is 1 times 10 to the minus 10 hydrogen ion concentration, the pH then would be equal to 10. Okay. How about B? POH. if POH equals 6.7, then pH equals 14 minus 6.7, which would be 7.3, right? Okay. And C is hydroxide. All right, so this is going to take a couple of steps. 7 times 10 to the minus 5. So POH. I can do that one in my head. 7 exponent minus 5. Take the log and then change the sign. So the POH is 4.15 and the pH would be 14 minus 4.5. Which would be 9.85. Okay, and D is already pH. And at least 2 of the solutions are equally basic. Do we have any that are the same pH? 4.2, 985, 7310? No. So E can't be it. So which one is the most basic? The highest pH. There you go. All right. Let's see, scroll to number 8. And maybe we can get 9 in there too. Yep. Which of the following solutions contains the strongest acid? Okay. You can tell, well, it depends on what that means, right? Strongest acid, right? The temptation is to interpret it as which one has the lowest pH. But in chemical terms, the strongest acid doesn't matter what the pH is. We're talking about the molecule itself. How far does the dissociation go? And the K determines that value. So if the K is a large number, then that one's going to be the strongest acid. So what do we have to choose from? We've got, well, let's take it top to bottom. 10 to the minus 10. 10 to the minus 5 is the next one, but it's also got a second. 10 to the minus 12. Is that going to have any effect on the pH for that one? The strength? No. No, it's too far away. It's a 7 orders of magnitude difference. Right? So we only have to focus on the first pK. Right? Minus 10, minus 5, minus 5. So if it was a tie between B and C, we would look to the coefficient to break the tie, in which case C would be stronger. But we go to D, which is minus 8, and E, which is minus 4. That one wins the prize. 10 to the minus 4 is the strongest acid in that bunch. HM. It's still a weak acid, but it's the strongest of that bunch. Okay. I think in the worked problems, I went to the trouble of calculating the pH for each one of those. I think I was just trying to make a point. But to answer the question, all we need to know is compare the Ka. Now, which one has the strongest conjugate base? Right, I just added that in there for discussion. The strongest conjugate base will be the weakest acid. So we look for the weakest acid, which is A. It would produce the strongest conjugate base. That is not the conjugate base. This is the conjugate base. And that would be the strongest of the bunch. Okay. Let's see. Number 9. Which of the following statements are true? Let's see. D and E, at least 2 of the statements are true, or E, all the statements are false. All right, so we got to look at each one of them, A through C. the pH of a strong acid is always lower than the pH of a weak acid. Is that true? No. Think of the K value or the pK of an acid as an intensity factor. It doesn't matter what the concentration is, it's still that value. But the pH is a capacity factor or an extensive property. It does depend on how much is there. Right? And in this case, the pH of a weak acid can be lower than the pH of a strong acid, depending on the concentration and the K values. Right? So this one's false. The pH of a solution can never be negative. Right? I think I showed you that one in class. All we need is one example that gives you a negative pH. Right? Let's say we have the negative log of hydrogen ion concentration of, I don't know, 1 molar. How about that? 1 molar. So what? Now that wouldn't work because 10 to the 0, that would be 0. Okay, how about 5 molar? There we go. Negative log of 5 molar. I'm gonna have to do that one in my calculator. Would be 0.6, 0.7 negative. So there we got one example, and all you need is just one to make that statement false. You can have negative pHs. And the reason for that is that the Sorensen's formula is just a mathematical expression, right? And it is what it is. For a conjugate acid-base pair, Ka equals 1 over Kb. Is that right? Ka equals 1 over Kb. No, no, it's you got to have water in there, and that's the expression. So this one's false. That means E is true. Right? They're all false.
Can we go back to 8 for a quick second?
Sure.
When you're talking about the strongest conjugate base,
Mm-hmm.
where B actually has that second dissociation, it's into negative 12, wouldn't that be the strongest? Because it's the
Yes, you're absolutely correct. That's right. I was focused on the wrong one. Right, because you will get some dissociation. Not much, but a little bit. And it will produce, let's see, it will produce C6H6O6. Like that. That's right. That's the strongest conjugate base out of that group. I'm busted. Let's see here. Get those two together. Left. For the stepwise dissociation of aqueous H3PO4. Okay. Which of the following is not a conjugate acid-base pair? So the first acid-base pair would be this one and lose 1 proton. That. The second one would take this one and lose another proton. And the last one, take that one as an acid and make the phosphate ion. Okay. So the A would be this one. B looks like that one. This one's A. This one's B. C would be, yep, that one. D would be False. And E is thrown in there because just to make the point that in all aqueous solutions, that's true, always. Right? So, yeah, E is true, A, B, C, and E are true, D is false. Well, for which of the following 0.1 molar diprotic acids with the second dissociation affect the pH significantly? All right. Actually, they're all the same concentration, so we don't have to worry about that. Right. For any of these, what's the rule? When does the second dissociation become significant? When the second dissociation constant is close to the first. So which one is really close? Well, A is 5 orders of magnitude, B is 4 orders of magnitude, C is 5 orders of magnitude, D is only 1. And not only that, for D, um, 1.8 times 10 to minus 3 and 9.3 times 10 to minus 4. And we can write this also as 0.93 times 10 to the minus 3. So that since these are the same power, now we can look at these two. They're relatively close. This is only twice as big as that one. The second dissociation would definitely influence the first. Now, I don't know if that's a real acid or not. Right? If there's an example of that, could be. Be hard to find, but maybe. But theoretically, D, the second dissociation would have an influence on the first, on the pH. All right. Who's next? 16. Which of the following would give the highest pH when dissolved in water to form a 0.1 molar solution? And we want the highest pH. Okay, what do we have? Strong acid? Strong acid. This would actually be the lowest pH of that group. A weak acid. A weak acid would still give a low, shouldn't say low, it would be an acidic. It would definitely be acidic. Right. Potassium salt of a weak acid. All right, if we have a potassium salt of a weak acid, it's going to dissociate into potassium and the conjugate base. Then that conjugate base is going to react with water to produce the acid plus OH minus. So this is going to be basic. Right. We're still looking for the highest pH. Potassium salt of a strong acid. Right. If we have the potassium salt of a strong acid, what's that going to do? Well, think of it this way. Potassium hydroxide is a strong base. If this is a strong acid, what are they going to give you? A neutral solution. If they're both strong, you end up at pH 7. And then the ammonium salt of a strong acid. So ammonium salt of strong acid. salt of a strong acid, like that. Okay, so that would produce this plus that. Then this is going to react with water like that. This is going to react with water, give up a proton. So they're going to be in the neighborhood. Neighborhood of pH 7. Depending on the, if we compare the, wait a minute. That's not right. That's right. If we compare the Ka of the, oops. I do it. Well, you know, I had it right the first time. It would dissociate into this and that. And then this would undergo its reaction, that would undergo its reaction. But this would have a Ka, this would have a Kb, and depending on which one was larger would determine if this is larger than that one, it would have an acidic solution. If this is larger than that one, we'd have a basic solution. Okay, so that's why I said it's in the neighborhood of 7. It could be below, it could be above, depending on the exact values. But it's not going to make a very basic solution. So the most basic solution would be this one. Weak acid, strong base. Potassium salt or weak acid. That would give you, out of this group, the most basic or the highest pH. Okay. Right. 16. Let's see, we're going to scroll to the next one. 19. Solid ammonium acetate. There must be more than one. Is it referring to? Okay, here we go. Select the answer that best describes an aqueous solution made from each of the following substances. Okay. Well, we can do them all because they're related. How about sodium nitrate? A qualitative expression, is this acidic, neutral, or basic? Right. Well, this would be derived from this salt, would be derived from sodium hydroxide plus nitric acid, right? Okay, that's neutral. Strong acid, strong base. Sodium carbonate. Right, this would be derived from sodium hydroxide and carbonic acid. This is a weak acid, that's a strong base, so this would be basic. And the last one, the one that's actually highlighted. Okay. This is ammonium acetate. So we've got, this one's derived from a weak base. This one's derived from a weak acid. So we need to compare the Ka of this acid, which is 5.6 times 10 to the minus 10. Ka for this acid, and the Kb for this one is exactly the same value. So there are no winners. This is neutral. Okay. Right, 19, 20. Solid ammonium perchlorate. Oh, is this still? Okay, we're still looking for the acidity or basicity of the solution. So if we put solid ammonium perchlorate in solution, and ammonia, we got the Ka for ammonia was it 5.6 times 10 to the minus 10, was it? Yeah. And the chlorate ion, the Kb for this ion in solution would be approximately 10 to the minus 21. Okay. This one is actually, we don't even need to know this, right? This is derived from perchloric acid, right? ClO4, which is a strong acid. That's derived from a weak base, strong acid. This just confirms the fact that this solution is going to be acidic. Okay. I don't even know how they got that value. That is a very, very weak conjugate base. And that stands to reason because this is a very strong acid. Okay. In fact, it's the strongest acid of the group of what? This one, that one, that one, that one. This is the strongest acid in the group because it has the most oxygens. Okay. All right, that was 20. 22. Which factor listed below is most important in determining the strength of an oxyacid? Oh, we just talked about that. Most important factor in determining the strength of an oxyacid is the number of oxygens. D, the number of oxygens atoms present in the molecule, determines the relative strength of an oxyacid within its homologous series. All right, 24. Which of the species below, when dissolved in water, will not produce a basic solution? Let's see, 24. And E, none of these. First one is SO2. Okay. So what happens to SO2 when we dissolve it in water? Okay. It produces H2SO3. It's an acid. Okay. This is also known as an acid anhydride when it's made up of a non-metal oxide. The second one is ammonia. Actually, it's ammonia. Excuse me. Ammonia. So when you dissolve that in water, it makes a basic solution. BAO. This is a basic anhydride, a metal oxide. So when you add that to water, let's see, what does it do? BaOH2. It's barium hydroxide. So that's basic. Oh, and if you happen to dissolve this one ready-made in water, right, it just produces, well, actually, yeah, this dissociation produces 2 hydroxyls. Right, this is a dissociation, acids are ionization. So when you put that in solution, it's going to produce 2 hydroxyls. So this is basic, that's basic, that's basic, that's acidic. It will not produce a basic solution. Let's see, we're still in chapter, yeah, we're still in chapter 14. Right, we got 3 in a row that are talking about Lewis acids and Lewis bases. Okay. All right. Let's remind ourselves. Lewis acid, Lewis base. So a Lewis acid does what? Well, Bronsted-Lowry acid donates a proton. And what does it do when it does that? It leaves electrons behind. So a Lewis acid accepts an electron pair, where a Lewis base donates an electron pair. When it accepts a proton, it donates electrons into the bond that bonds the hydrogen to it. So it's donating an electron pair. It's a Lewis base. Okay, now let's go to the problems. Which of the following species cannot act as a Lewis base? In other words, which one cannot donate electrons? O2. O2 minus, yeah, it's got plenty of electrons. We could draw the Lewis dot structure for that, I guess. Oxygen would be, let's see, valence would have 6. And then you add 2 more, and that makes your 2 minus charge. So yeah, it's got plenty of electrons. How about OH minus? Yeah, it's got donating electrons, donatable electrons. How about CH4? Well, CH4 has no electrons to donate. They're all tied up in bonds. So this one would not be a good choice as a Lewis base. H2S, right? H2S, we drew the Lewis dot structure for that one. Let's see, sulfur, this has 6. 7, 8, we took away 2, so there's 6 more. 2, 4, 6. Is that right? Yeah. Okay, so this one has a lone pair of electrons it can donate. And then ammonia. What does ammonia look like? Remember, it's Lewis structure. I've got a hydrogen in the back, got hydrogens out here. They form the base of that pyramid. And then we have a lone pair up here. So it's got electrons to donate too. So it would be a valid Lewis base. How about 26? We're still looking for one that cannot be a Lewis base. All right. Let's see. No. In 3 minus. Got lots of extra electrons. NH2, 2 minus. NH. Oops. There we go. Minus. We still got extra electrons. Those are all valid bases. This one's a valid base. We just showed that one. And then This one is ammonium. It has no free electrons. You just replace this one up here with a hydrogen and a positive charge, and you have no available electrons to donate. So this one would not be a good choice as a Lewis base. Okay, which of the following cannot act as a Lewis acid? So we want something that will not accept electrons. All right, potassium, oh yeah, it'll pick up electrons. Magnesium, no problem. Aluminum, oh yeah, loves electrons. Hydrogen, yeah, it'll pick up electron. H minus, never. That one's got no more room for electrons, right? It's 1s shell is full. So that would be not a good candidate for a Lewis acid for accepting electrons. I think I scratched 28 out of there because it was confusing. So we'll not worry about that one. About 30. Let's see, what are we into here? Oh. 30. This one should be fairly easy. Which one of these, based on its value of pKa, which is the weakest base? The weakest base in that list, right here, based upon the pKa's of these. So the weakest base would be the strongest acid, right? So the strongest acid would have the smallest pKa. HClO2 would produce Cl2 minus would be its conjugate base, right? Cl2 minus is in there, yeah. But we've also got Cl minus in there. And we don't need a Ka for this one because it would be derived from that one. And that would be an extremely weak base because it's derived from a strong acid. Right? So that's kind of tricky. Right? If you focus only on that list, then you're going to say ClO2 minus. But if you notice at the bottom when it's Cl minus, it's derived from a strong acid. That's a very, very weak base, even weaker than ClO2 minus. Let's see. Yeah, a lot of repetition. Okay, 38. Oh, by the way, when we get to 39, did your copy of chapter 14 worked problems have number 39 in it? I didn't think so. So I've added that one to the Brightspace version, and we're going to do it on the board too. So, but let's do 38 first. All right, carbonic acid is a diprotic acid with Ka1 10⁻⁷ and Ka2 10⁻11. The ion product with water is 10⁻14. What is the OH minus concentration of a solution that is 0.18 molar in sodium carbonate? All right, so we're given Na2, CO3, and it's 0.18 molar, 0.18 molar, right? So what is it going to do in water? It's going to produce that and this, right? And it's going to have Is sodium going to react with anything? No. Sodium hydroxide, if you think of it in those terms, completely dissociates and they don't get back together. Sodium does not react with water at all. So we're only interested in this one right here. So if this is 0.18 molar in CO3, then it's also going to be 0.18 molar in CO3 2 minus. Okay. All right. Let me see. So what's the controlling reaction? This is a very weak acid, and its strongest conjugate base is going to be CO3 2 minus, right? Plus H2O yields HCO3. Oops, 1 minus. There we go. Plus OH minus. Okay. Now we're given the Ka of this one, 10 minus 11, and we're given the Ka for H2CO3, which is 10 minus 7. So which one controls the reaction? Well, if the Ka for this one, Ka2 is equal to 4.8 times 10 to the minus 11, then what's the Kb? Because the Kb is this one, and actually it's going to be Kb1 because we're going the other direction. And so that this one's going to be 1 times 10 to the minus 14 divided by 4.8 times 10 to the minus 11. So that Kb is going to be 4.8 exponent 11 divide 2.08 10 to the minus 4. Right. Now, what if we wanted to look at this one when it reacts, CO3 minus plus water, because this will happen, but is it significant? Is it going to influence the pH at all? Is it going to influence the hydroxyl concentration? So this will give us CO3, so H minus, and the Kb for this one is going to be 1 times 10 to the minus 14 divided by 4.2 times 10 to the minus 7. Right? 4.2 times 10 to the minus 7. All right, so let's see what that one is. This is 2.38 times 10 to the minus 8. Right? Is that going to have a significant impact on the hydroxyl concentration in this solution? -8 versus -4. No. This is the controlling reaction. This is the one that produces the measurable hydroxide concentration. So we don't even have to consider this one. We can just throw that one out. Got it? Okay. I'm going to erase this part. All right. So if we've got 0.18 molar in this one, 0.18 molar, and we essentially have 0 here and 0 there, then the change is going to be that direction. We're going to lose some of this, and for every one of these, we get one of those. Okay. So now we're going to have 0.18 minus x, and this is Kb, right? So we have the Kb value here. This is 2.08 times 10 to the minus 4 equals x times x over 0.18 minus x. Now we have to ask ourselves, is that number small enough so that the appearance of x can be ignored, right? And I'm going to cheat a little bit. Let's see. Look at the 38. Yeah. In the work problems, I actually did the 5% rule calculation and it came out 3.4%. So we're safe in saying this is approximately x squared over 0.18. So x is going to be square root 0.18 times 2.08 times 10 to the minus 4. 0.18 times that. So that value is 3.75 times 10 to the minus 5. And x is what? We chose x to be the hydroxyl ion concentration, which is the answer. So if I do the square root of that, I should get the answer. 6.12 times 10 to the minus 3 molar hydroxyl ion concentration. 6.1 A. A is the closest one to that. Okay? So the trick to this one is trying to figure out what's the controlling reaction. And that's what we did with the calculation of the KBs and found out that the first reaction is the controlling reaction. All right. That's 38. Now we'll do 39. You're on time. We're good. We're good on time. All right, let's see. Yeah, we can read it up there. All right. What's the pH at equivalence for the following titration? So we're going to titrate hypochlorous acid with sodium hydroxide. What's the reaction? The reaction is hypochlorous acid plus sodium hydroxide. We're going to equivalence, right? So we're going to go all the way. And it's going to produce sodium hypochlorite in solution plus water, right? Always acid, base, salt, water. Okay, the concentrations here, we're starting off with 0.1 molar and 0.1 molar. Okay. All right, we're going to equivalence. So that means all of this is going over here. But we're going to do this in two steps. One is the stoichiometry. That is, what is the mole balance here? Well, the mole balance sends it all to that side. But we can't go over there in concentrations. We need molar values. Well, since these are equal concentrations and each molecule has hydroxyl here and one hydrogen here, then all we need to do is calculate the number of moles based upon an equal volume. Since they're the same concentrations, we're going to need an equal volume of each one. So we can pick any volume we want. I picked 100 milliliters. How about that? 100 milliliters of each would take us to equivalence. Okay, so that would be what? 10 millimoles here and 10 millimoles there, right? So this is before and after. So after would be what? We get 0 here and 0 here. Before would be 0 there, and whatever that is. And we're gonna have 10 millimoles here. And now we can calculate the concentration of this species. So what would be the volume? Well, 100 milliliters plus 100 milliliters, right? So 200 milliliters here will give us what? Well, it should give us 0.05, right? 0.05 molar. All right. Let's see. 10 divided by 200 is 1 divided by 20. Yeah, 0.05. Because 1/2 would be 0.5, and then 1 divided by 20 would be 0.05. So this is our starting position. This is the stoichiometry. Now we're going to do the equilibrium. And this calls for an ice table. It calls for a new controlling reaction. What do we got here? When this is in solution, it produces what? Sodium ions plus hypochlorite ions. That's what we're interested in right there. So the hypochlorite, let's see, I'm going to run out of room. Hypochlorite ion reacts with water and then establishes an equilibrium between this side of the equation and hypochlorous acid plus hydroxide. There we go. So now we can set up our ice table. We're starting off here with 0.050 and essentially 0 here and here. Okay, so what's going to change? Well, for every one of these, you're going to produce one of those. That means we're going to lose an X here. We're going to add an X here and add an X here. So we have an X and an X. Down here we have 0.050 minus X. Okay. The problem is, what's the KB? Right? This is a base reaction. We got the Ka, 3.5 times 10 to the minus 8. So the KB for that reaction is going to be divided by 3.5 times 10 to the minus 8. Let's see. Divided by 3.5, 10 to the minus 8. Here we go. 2.86 times 10 to the minus 7. There's the KB. And so our expression here is going to be 2.86 times 10 to the minus 7 is equal to X squared over 0.050 minus X, which is approximately X squared over 0.050. And we're throwing the X out because it's very small. And we're pretty safe there because this is a minus 7. All right, so X is equal to the hydroxide ion concentration, which is equal to square root of 0.05 times 2.86 times 10 to the minus 7. 0.05 already in my calculator, so I just multiply by that by 1.43. That's 8. And square root of that is 1.20 times 10 to the minus 4. And what was the question? What's the pH? Right. So let's calculate the pOH. Take the negative log of that value. 3.9, let's see. 3 significant figures down to here. 3. So that means I need 3 decimal points in pOH. 3.923. And the pH equals 14 minus 3.93. Change the sign. 14. So I get 10.007. Right? No, 10.07. So 10.1 is probably the closest to the answer there. So this is one of those problems where we do it in 2 steps: stoichiometry, equilibrium. And the stoichiometry is because we're doing a titration to equivalence. We got to go all the way. If you only go part of the way, then next chapter, we'll learn how to use Henderson-Hasselbalch to solve the problem. Okay, that's the last of chapter 14. Now we're going to go to chapter 15. Am I erasing something you need? Oh, okay. All right. Chapter 15. So let's see, I need to stop this share. Come on. Stop the share. There we go. And I'm going to share chapter 15, which is right here. There we go. And let's see, let's bump this up to maybe 200. And scoot it over. About that. There we go. All right, let's scroll down here. Is it still down here, right? Yeah. Okay, we're going to pick up chapter 15 on number 4. And looks like I get 4 and 5 together. Okay, chapter 15. We're getting into the buffer zone. A weak acid, HF, is in solution with dissolved sodium fluoride. So we got HF in aqueous solution, and we got sodium fluoride in aqueous solution together in that same solution. If hydrochloric acid, HCl, is added, which ion will react with the extra hydrogen ions from the HCl to keep the pH from changing? All right, so we look at the equation this way. We've got fluoride ions and HF. HF, and I'm going to use the abbreviated version. We got hydrogen ions here and fluoride ions there. These are all aqueous. Okay, if we add hydrogen ions to this solution, what's it going to react with? Right there. It's going to react with fluoride, right? And shift the equilibrium back to the left. So C is the answer. Right? C. Hydrogen ions react with fluoride ions. Okay, number 5. Let's see, no. And it didn't show up. Okay. Which of the following is true for a buffered solution? Let's see. How about A? Does the solution resist change in hydrogen ion concentration? Yeah, that's pH. Yeah, that's true. The solution will not change its pH very much, even if a concentrated acid is added. Another way of saying A. The solution C will not change its pH very much if a strong base is added. That's also true. Any hydrogen ions will react with a conjugate base of a weak acid already in solution. That's true as far as it goes, right? But we already know that we can make buffered solutions with weak bases too, right? But that statement in and of itself is true. All right, so all of these are true. All right, that's 5. Uh-oh. Got to plug it in. Well, the battery goes dead. Don't do that. There we go. In the nick of time. 8 and 9, got both of those. How do the pHs of the buffered solutions compare? Is that referencing a former statement? Yes, it is. All right, so let's stick with this one. You have 2 buffered solutions. Buffer 1 is 5 molar acetic acid and 5 molar sodium acetate. So buffer 1 is 5 molar acetic acid and 5 molar sodium acetate. So that puts the weak acid and the strong conjugate base in solution at the same concentrations. That's right in the middle of the buffer zone. And so that's a good buffer. How about buffer 2? Buffer 2 is 0.05 molar, 0.05 molar of the acid and 0.05 molar of the base of the conjugate base. Right. So what do we know about those 2 solutions? Well, if we look at Anders and Hasselbalch in generic terms, as long as the pKa is a constant, so as long as the ratio of this one to that one is the same, you'll have the same pH. So the ratio here is 1, the ratio here is 1. These 2 will have the exact same pH. The pH of buffer solution 1 is greater than that. Nope. Buffer solution 2 is greater. Nope. pH of buffer solution 1 is equal to that of buffer solution 2. Yes. And we can determine the value. So C is the answer to this one. They're exactly the same pH. All right, number 9. Which of the following is the net ionic equation for the reaction that occurs during the titration of nitric acid with potassium hydroxide? Nitric acid plus potassium hydroxide makes what? Makes the salt, potassium nitrate, which is soluble, plus water. Okay? This is okay. So when we talk about net equations, we go through a sequence of complete ionic equation. This is already balanced, you can tell. It's balanced. Complete ionic equation will separate these guys out. And I'm leaving out the aqueous for convenience. These are all in aqueous solution except for water. It's still liquid. Okay? So the net ionic equation will simply take the ions from both sides. If they're the same on both sides, they cancel. Okay? and nitrate cancel. What's left? Right, that's the net ionic equation for an acid-base reaction. E. Okay. Number 10. Okay. In the titration of a weak acid with 0.1 molar sodium hydroxide, the stoichiometric point is known to occur at pH value of approximately 10. So stoichiometry says the equivalence point occurs at pH 10, approximately 10. Which of the following indicator acids would be best for the use to mark the endpoint? So which would give us the best endpoint here? The endpoint would be for the indicator that has a pKa at approximately 10. That's where it changes from the acid form to the base form of the indicator. All right, so which one comes closest? Well, the pK, of course, is going to be the negative log. So we just take the negative log of each one of those, and you got your choices: 14, 11, 8, and 6. So I would pick this one right here, B, because it's closest to the pKa, or the pH at the equivalence point. Also, remember when we're titrating a weak acid with a strong base, right, what are you going to see? Well, it's going to start off at a low pH and go up a little bit, and then it's going to flatten out. And it's going to go up like that, flatten out again. So this is added base. So the indicator, we want the indicator to change here like this. That. And if this is pH 10, and this changes at pKa or pH 11, then it's going to change up here somewhere, right in that region. Remember that the human eye is plus or minus 1 pH unit. So this change will occur between 10 and 12 pH. So we're going to see it when it first changes right here. If we were titrating a weak base with an acid, a strong acid, the curve would be the other direction. Right? It would go like this. It would go, so, pH would drop fast and level off, and then it go like that. Well, in that case, you would want the pKa to be on the other side so that you catch it early. We're catching it early here because of this 10 to 12, right, with a pK at 11. But if you go in the other direction, then you would probably want maybe a pK of 9 would be a better choice if it's available. Okay, that's just a practical application. But to answer the question, B would be the best answer for 10. And of course, if it's a multiple choice, then you pick the best answer, whatever you have available. Which of the following solutions would be described as a buffer solution? This is 13. All right. What we want is as close as we can get to weak acid conjugate base concentrations to be equal. That's perfect. And which is any one of these close? Well, let's see. The first one has 0.25 molar acetic acid. And 0.2 molar HCl after we've added them together. Right, this is going to be close to the stoichiometric point. You've almost used everything up. That would not be a good buffer. How about B? 0.25 again, plus what? Plus 0. Well, no. Scratch that first explanation. You're adding an acid to an acid, right? There's no buffer potential there at all. But 0.25 molar acetic acid and 0.2 molar sodium hydroxide would do what? Well, it would use up almost all of the acetic acid, but you'd still have a little bit left over. You'd have 0.05 molar left over. So you have 0.05 molar C2H3O2, and then you have 0.2 molar acetate. Right. So that would be on the tail end of the buffer's region. So that's possible. C, sodium bromide and hydrobromic acid. Is that going to work as a buffer? No, hydrobromic acid is strong acid. Right, so it doesn't matter how much conjugate base you mix with it, it's not going to act as a buffer. Right, so that was out. 0.25 ammonia and 0.15 sodium hydroxide. That's like this one. You're adding a base and a base. You're not going to get any buffer out of that one. And then E, hydrochloric acid and sodium hydroxide. There's no weak acid in there. Right? Hydrochloric acid, strong acid, sodium hydroxide, strong base. If anything, let's see, you're only neutralizing part of the acid, so it's going to be a low pH. You're going to have acid left over. Right, so this is not going to be a buffer. Out of those, the best choice is this one. It's not a good choice, but it's the best one. Okay. All right, 14. All right. Which of the following mixtures would be classified as a buffer? Okay. So we got A, B, C, D, and E. So what do we see in A? We got a strong acid and the salt of that acid. Nope. Won't work. You gotta have a weak acid. Okay, B is a weak acid. And it's we're adding the same amount of hydroxyl as we have hydrogen ions. Remember when I wrote, this is acetic acid. This is another way to write acetic acid. It's the same as HC2H3O2, or if you write some structure into it, C like that, and there's your acidic hydrogen. So that there be no confusion, that's acetic acid. Sometimes you may see it written this way, HOAC. So that's the acetate ion, and that's the hydrogen. Right. I'll try not to write it that way, so maybe any confusion. All right, so we've added enough base to neutralize all of the acetic acid. Right. We're past the equivalence point, because you got 5 mils of sodium hydroxide past the equivalence point. It's going to be a very high pH and not buffered. How about the next one? All right. We're only adding half of the sodium hydroxide needed to neutralize that acetic acid. Yeah, that's perfect. That's right in the middle. of the buffer region. 50 milliliters of acetic acid and 0.5 milliliters of base. You're still on that part of the curve that's down here like that. You're down here somewhere. Right? You're nowhere near the buffer zone. So D will work. And E, if you add acid to acid, you're not going to get any buffer. So C is the best one. In fact, C is perfect. It's right in the middle. All right. Let's see. 19. All right. Consider the following indicators of their pH ranges. So in this case, we're not giving you the Ka of those indicators. We're telling you this is the pH range that's most useful. So it's like it came off that last chart in the PowerPoint with the colored regions. Pull these off of there. But we're only interested in one of them. Which of the following titrations would methyl red be the best indicator? So methyl red changes color on the pH range of 4.86 to 6.0. Right, that's its pH range. So which one of these would work best? Well, A is a strong acid, a strong base at equivalence. This is going to be neutral at equivalence. Right? So this changes color below that region. Right? So that's no good. How about B? Aniline and HCl. Well, okay, we're going to titrate aniline with HCl. So where does it change pH? That's the question. So we have to set up. Let's see. Did I do this already? I think I did this one. I did all the math in the. Why am I skipping the 19 already? Hold on a second. Okay, we did all those, right? Oh, okay. Sorry. Let's see, I want to be sure. All right. This would take a good bit of time, I think. There's 19 start. There's 19 starts there. Okay. All right, in order to answer this question, we would have to, let's see if I can do this semi-qualitatively. 0.1 molar aniline and 0.1 molar HCl. The hydrogen chloride, the hydrochloric acid would completely neutralize aniline, and it would be at the equivalence point. But what's the pH when you add a strong acid to a weak base? This is going to be very acidic. Okay. So well below that value. And the work problems tells you that it's actually 2.94. Right, so that proves it at equivalence. So this one won't work. See, somebody show up or somebody disappeared. Yep. Somebody disappeared. How about the next one? 0.1 molar ammonia and hydrochloric acid. All right. So if our Kb is 1.8 times 10 to the minus 5, that says that NH3 plus HCl yields NH4 plus Cl minus. And we're going to have 0.1 molar, 0.1 molar here before. This is like that problem we worked earlier. And after, we're going to have 0.1 molar here. No, we're not. We're going to have 0.05 molar. Because we add equal volumes of these two, we're going to cut this concentration in half. There we go. And the Ka, let's see, is there a better way to do this? No, we would have to do that. The Kb for this one is equal to 1.8 times 10 to the minus 5. That looks familiar. That's the same as the Ka for acetic acid. But the Ka for this one is going to be 10 to the minus 14 divided by 1.8 times 10 to the minus 5. Right. So let's see, I've already got it here. No, I didn't write it out that detail. Exponent 14, 1.8 exponent 5 divided. So that's 5.56 10 to the minus 10. Okay. So now we're gonna do this one at ammonium is going to produce ammonia plus hydrogen ions. And we're starting with 0.05 here, 0.05 molar here as the initial change exponent. We're going to minus x here, we're going to plus x here, plus x, 0.05, minus x, and then x and x. So what we've got here is a similar situation to that earlier problem where 5.56 times 10 to the minus 10 is equal to x squared over, we're going to drop to x, 0.05. So x is going to be the square root of 0.05 times 5.56. 2.78 10 to the minus 11. And the square root of that is 5.27 times 10 to the minus 6. And then the pH at equivalence is going to be negative log of 5.27 times 10 to the minus 6. Log can change the sign. 5.3 roughly. pH. 5.3 puts it right there. So I think we found our answer. Now we can do the others. HF and sodium hydroxide. Weak acid, strong base, that's going to be basic. Right? Yeah, D. If you have a weak acid and a strong base, then at equivalence, it's going to be basic. Right? So it won't fit in this region. And E, acetic acid and sodium hydroxide. Right? Same thing. HC2H3O2 plus sodium hydroxide, that's also going to be basic. Okay. So I suppose by process of elimination, we could have come up with this one without having to go through all that. Because we know this one's going to be acidic, this one's going to be neutral. Those two are basic. So the only one left is C. It's just, we proved it. Anybody have any trouble with that? Okay. 19. Okay, we're good. I think this market needs a rest. See if one of these works. 19. Next. How about 23? $50 milliliters of 0.0350 hydrocyanic acid titrated with 0.033 molar solution of sodium hydroxide. What's the pH of the acid solution after 15 milliliters of titrant has been added? Okay, they're telling us it's an acid solution at this point, which is helpful. Okay, so what's the controlling reaction? Well, let's see, we have hydrocyanic acid and sodium hydroxide. Hydrocyanic acid plus sodium hydroxide, and these are all aqueous, I'm just not going to write it in there. And that produces sodium cyanide plus water. Okay. All right. We're starting off. This is before. We're starting off with HCN at 50 milliliters of 0.035 of 0.0350 molar and 50 milliliters. And we're titrating that with 0.0333 molar sodium hydroxide. 0.033 molar sodium hydroxide. And 15 milliliters of this one. Okay. All right, so after what do we have? Well, how many moles of this do we have here? Or millimoles, that'd be easier to calculate. 0.035 times 50 is 1.75 millimoles. And this is one hydroxyl and one hydrogen. So the stoichiometry is 1 to 1. And then 0.0333 times 15 is 0.4995 millimoles. Okay. So when we add this one to that one, what happens? This one gets all used up, right? Completely used up. 0. This one, on the other hand, we just subtract 0.4995 from that value, and we get 1.2505 millimoles left of this. But where did this go? Well, this amount ended up over here. So this after and this after 0.4995 millimoles. There. So that's after. What's the concentration? That's a good question. This is millimoles divided by milliliters is molarity, correct? Okay. So divide this by the total volume. 50 plus 15 is 65. All right. So the concentration, I'm not doing good either. The concentration is, let's see, I can take this one. I've already got it in here, so I'll say 65 divided into that. This is 1.92 times 10 to the minus 2 molar. And this one is 0.4995 here and 65. This one is 7.685 times 10 to the minus 3. Okay. Now what's going to happen? Well, we're going to have we've got all of this base is gone. We just have this conjugate base, right? And this acid, weak acid here. And we have the Ka of the acid. Guess what? We just need this concentration, that concentration. So what's the pKa? The pKa of 6.2 times 10 to the minus 10 minus log of 6.2 times 10 to the minus 10 equals. See where I'm going with this? Take the log of that, change the sign. 9.208. This is my last either. All right. So let's go back to this one. All right, so the pH is going to be 9.208 plus log of Cn minus 7.685 times 10 to the minus 3 divided by 1.92 times 10 to the minus 2. There we go. So let's see. My calculator, I can scroll that. I'll put this one on top, swap it, and divide. So this part right here, this right here is 0.3994. I need to take a log of that. Right? So the log of that is minus 0.39. So that's subtracted from 9.208. Is pH 8.81. Okay. Henderson-Hasselbalch to the rescue. What we had to do is figure out, this is before, when we ended the titration, this gives us the value of our weak acid and conjugate base. And then you can fit Henderson-Hasselbalch into it. Okay. That was 23. All right. 25, an indicator problem. A certain indicator, HIN, has a pKa of 9. In with a pKa of 9.0, correct? Yeah. A color change becomes visible when 7% of it is IN minus. So we've got an equilibrium here set up with that. And the ratio of this to this is 0.07. Right? It's 7%. Let's see, is that worded? Is that worded correctly? 7% of it is in IN minus. Because you could read that two different ways. Right? Is this the ratio? If we had, say, IN minus ratio to HIN, we could say that that's equal to 0.07, because that's the decimal equivalent of percent. Or would we have to say 0. Well, 7% of it is this, and the other 93% is that. You know, it's a matter of interpretation. Let's work it both ways and see what happens. Okay, so we'll work it the first way where we're saying, all right, the ratio of these two is 0.07. Right, so we have log here, and we have pKa here, and we have pH there. So this would be 9.0. This value here would be 0.07. So the log of that value, log 0.07, is minus 1.15. And that makes the pH equal to, let's see, 5, 8. Or is that 7? That's 7. Right. Yeah, 7.85. All right, so that answers the question the way it was intended to be in that format. But what would happen? I'm just curious. What would happen if we worked it the other way? If we say, all right, if 7% of it is in this form, then 93% of it is in that form. So this would be 7 divided by 93. That's what's left over. So what would that do? 7 enter, 93 divided. This would be 7.53 times 10 to the minus 2. Right? Then we take the log of that. Log of that. And that value would be minus 1.12. And then 9 plus that would be 7.88 rounded off. So it would make the pH a little bit higher if we interpret it some differently. But in either case, well, I guess since there's none of these, you could argue that that was the case. Need to word the question better. 25. Let's see what's next. 26 and 27. Let's see. 26 and 7 are referencing the this titration curve down here. So let me see. Let me see if I can move it over just a little bit. Yeah. Let's shrink it because I want to see the whole thing. Come on. It's not responding. There it is. About 150. Not quite. Let's go to 125. There we go. All right, so there's the titration curve. Notice this titration curve has how many buffer regions in it? Right? You don't count the top one because that's beyond. So it's got 2 buffer regions, right? One is at B and one is at D. B buffer region is in the neighborhood of maybe 2.5, 2.3 pH. And the second one is in the neighborhood of maybe 9.5 pH. The first equivalence occurs at pH 6 at C. And the second equivalence occurs at almost 12 at E. Okay, that's how you read that graph. Now let's go back and see what 26 and 27 are asking for. All right. 26 is asking for pH at first equivalence. First equivalence, okay, and 27 is asking for best be used in the buffer near pH what? Okay, so I'm gonna write all these so I can scroll down to the other one. A, B, C, D, E. I might as well write these in here too. So A is 1.2 and 2.3. And 602. 969. And 1185. Okay, and then the second one is 1, 4, 6, 10, and 12. 6, 10, 12. Yes. And these are all pHs. Okay. So let's see, 27 was best buffer. Okay, now let's go back down to the figure and answer this question. Which one would be the best first equivalence? First equivalence occurs at C, which is pH 6. This would be the best. Okay. Best buffer. What do we have to choose from? 1? No, I don't think so. 4? No, 4 is past the first one. 6, that's equivalence. 10 looks good. 12 is too high. 12 is the second equivalence. So 10 would be the best choice for buffer out of this molecule. Okay.
Would you use that one because it's between the two equivalence points?
This one, 10.
Yes.
Yes. Right. You've already had an equivalence here where you have let's see, HA minus. Now you're on to the second one. It's given up another hydrogen and it's going to A minus. So this one would be buffer. The best balance between these two is at pH. Well, actually, the best balance would be less than 10, but 10 is a good compromise. It's on that flat, relatively flat region. Some of them, it varies. Some of them are really, really horizontal. And then some of them sort of slope a good bit. Okay, that was 26 and 27. Let's see what else is waiting in the wings. Nothing. That's it. Oh, we're done early today. Any questions before I stop that share? Okay. We lost Aliana.
She just dropped out a few minutes ago. Whenever you said someone disappeared, that was her.
Yeah. And we never got Kayla.
Nah, I didn't figure. She told you she never texted me back or anything.
Yeah. She's either working or can't find somebody to watch her kid.
Yeah, probably.
We're having internet issues in Greenboro County, so mine went out for a little bit too.
Okay. Okay. I see. Well, that's a good thing we recorded, huh?
That's it.
Okay, I'm gonna stop the share and we're done for the day. On Thursday, we'll have a test on this material, and right after that, we'll jump into chapter 16 and learn about solubility. Solubility products and complex ions, so that we can do the lab afterwards. I'll give you a copy of the lab on that day, Thursday.